Okay, Professor Fatalian is off on a research-related trip right now, so I'm going to give the lecture today. The story on this particular song is I'm old enough to remember when it was a #1 hit. Today what we're going to talk about is we're going to continue on this idea of coherent memory systems. Let's see if we can improve the lighting. Maybe this doesn't. Yeah, if we could turn off these ones right on the screen. So you recall the idea is that we're looking at systems. You've got, well, that's you're 50% there. That's the other 50%. There, good. So the idea is how do you build systems where all the processors have a view of a shared memory space that they can all access and all have some reasonable notion of coherence. That if one of them writes and then another one reads, that there'll be some ordering, some reasonable ordering in how the programs execute on the two different machines that are what you heard about, the idea of serializability. There's some way you can view it as two different threads executing, and they might be interleaved, but they're not inconsistent with each other. And this is an extremely valuable programming model. If you think about it, it's what you've had if you've ever written a code using P threads on a regular CPU, or if you've, the CUDA programming you did, although it was a little bit tricky dealing with memory consistency, at least there was some notion of consistency, and at least there's sort of a shared memory that you could fetch all your data structures across. And similarly, in the programs you're writing now for assignment 3, those are all based on shared memory. So this is a pretty convenient programming abstraction, but not always so easy to build the hardware and all the support structure to make it work. So last time we saw ones that are based on what they call snooping caches. And today we'll talk about ones based on a more distributed structure than that's designed to scale better for larger configurations. So some of the things that we're going to talk about then are scalability, and that's sort of a core principle in all of systems. It's great to have a system with only 4 processors, but really we'd like 100 or 1,000. And so we'll talk about directory-based schemes. And what we'll find is it's really hard to actually come up with a scheme that works and doesn't require, that has sort of a combination of reasonable amount of resources and also reasonable complexity, something that could work fast enough to be useful in practice. Because these things have to work pretty fast. You're talking at the memory latency speeds of a system. So really you want to be down in the sort of low microseconds at worst for retrieving a byte of memory from some remote memory part of the memory system. So it pretty much all has to be done in hardware. You don't have a lot of time for software in there. And it has to be, and that's, you'll see that's not an easy thing to do. We'll also see that it actually depends a lot on how you organize the communication, has a big impact on both scalability and the sort of complexity and of the resources involved. So last time we were looking at ones that are sort of a bus-based concurrency, that there's some notion of a bunch of processors sharing some common interconnect, typically a bus. So a bus being, just think of it as a single point where all the communication is passing through that point. Physically, of course, it's distributed as a wire, but logically that wire is just one signal. And you're just sharing that bus, and basically the processors are contending with each other for that bus to get across to the memory system. And I'll just point out that this is a somewhat simplified view. In reality, what typically happens is the processors will have 2 levels of local caching, L1 and L2 on them. And then there's also buffering the memory system, a shared L3 cache that is, so shared meaning it's used by all the processors. So it actually kind of sits right here in the memory system. And the actual coherency happens between the the distributed L2 caches that are private to the processors and the shared L3 cache that's common to all of them. But logically, that doesn't matter how we, if we break things up into more levels of cache. The point is there has to be some way of getting between a place where you have multiple copies of potentially of a single line of the cache and one where there's only a single line of the cache. And how do you keep consistency across that? So we don't have to go into any more detail on levels of cache than this picture shows. The idea that was presented was the idea of snooping, meaning that basically all the processors are sort of watching the bus. And when transactions go across, they might actually jump up and do something, even though they're not on behalf of their copies in their cache that's unrelated to whatever their processors happen to be doing. So in particular, you remember we'd get multiple copies of a given cache line potentially spread across a number of processors. And then when a transaction would come across on the bus saying it wanted to either read or do an exclusive read on that cache line, then these local caches would jump up and potentially supply the data, potentially invalidate their own copies, or change the state associated with their copies. So those schemes are fairly common and pretty much ubiquitous in all multi-core processors nowadays and have been for about 20 years or so, since multi-core came along. More like 10 years, I guess. So that's pretty routine nowadays. And the thing about it is the scheme, because there's this single point of communication, basically all the cache controllers can kind of see all the traffic that's occurring regarding all the different lines of memory. And so they can track and detect when something is special is going on. So one step above that is to say it's often convenient, rather than having memory sitting as a big monolithic chunk on the other side of the interconnect, to have memory that's associated with the individual processors. And the advantage, this is sometimes called NUMA, meaning non-uniform memory access. And the idea being that there'll be some memory locations that are more directly accessible by the processor than others. And if they have to, there's still this notion that you want this entire memory space to be viewed as one coherent address space, and basically different addresses mapped to different ones of these memories. But that there's a non-uniform access, meaning that a processor can get to its local memory faster than to other memories. And potentially, if you can write your applications the right way, you can take advantage of that locality to put stuff that you're going to need sooner closer to the processor. But as you can imagine, that's a big pain in the neck from a programming perspective. But this is still a somewhat more scalable design in that now we can pretty much just have a bunch of processor boards that plug into some type of backplane that forms the interconnect. So these are sometimes this class of systems we're describing is sometimes referred to as a CC-NUMA, cache coherent NUMA. So the problem is still this question of interconnect. If this interconnect is only connecting, say, 4 or maybe pushing it to 16 of these processors, you can imagine a bus being able to handle that. But if you try to go beyond that, and 16 is definitely pushing it, you just have way too much traffic on this bus to be able to sustain the type of rates you want. And you get a rather poor performance that when you're local, it's good, but the access time and the bandwidth limitations of that interconnect mean that everything that's not in the local memory will be quite far apart as far as time goes. So it's not a very scalable design. So one thing would be, okay, well, what can we do with the interconnect to improve on that. And one is to become hierarchical and basically create a tree of buses, relying on the fact that, again, we have this sort of layers of locality, that some things are very local and some things are sort of to closer memories, and there's ones that are further and further apart. So we sort of add to the levels of cache hierarchy also levels of memory hierarchy and how far away they are. And we hope that somehow the amount of traffic that crosses the sort of central bus of the system is a less, some fraction of the total system communication. And sometimes these are done in a sort of heterogeneous fashion, where at the lowest level you'll have something that looks like what we saw earlier, is a bus-connected set of processors all with one common memory. And then there's a larger, sort of more global bus that spans across systems. And then we have to worry, though, about the coherence questions, that maybe on this localized thing they can use these snooping protocols. But how do they kind of maintain coherence and consistency of the caches across those? That's not an easy thing. But there are systems that look this way, and we'll talk about some. So the challenge of this, of course, is that this can potentially become a bottleneck. And also, there's a sort of interest in other topologies. Anyone know what this topology is called? Yes. It's a hypercube. It's like a cube in 4 dimensions, right? So if a cube in 1 dimension is a line, and a cube in 2 dimensions is a square, and a cube in 3 dimensions is what you think of as a cube, then beyond that, it's called a hypercube, and this would be in 4 dimensions. So, and there's actually an era in which people were building systems that were up to 1,024 node hypercube systems, and then discovered that it's really hard to run the wires of a system that's more than 3-dimensional in a 3-dimensional world. So nowadays, these are basically scaled up to be more of a three-dimensional mesh structure. Anyways, there's other topologies we might want, and a hierarchical system is not necessarily such a great system. So what we're going to move to is an idea, instead of this snooping, or essentially that there's a single point at which all traffic passes, and we can observe, or essentially we're getting a broadcast capability. All the nodes in the system are able to see all the traffic. We'll do it more based on a directory, where we store information in a set of directories distributed across the system that describe where the different copies of a given block of memory are residing. And so these are called directory-based schemes. So let's look at one very simple version of this. And so imagine that we have one node in the system is a processor, it's got a cache, and it's got some fraction of the overall global memory of the system. And of course, we'll think of this memory as being divided into lines, and let's say a line is 64 bytes. What we'll do is we'll also have a directory where for every line of this memory, we'll also have an entry in this directory where these little boxes are basically bits. And they correspond to 1 bit for every other processor or every other node in the system. And it will be set if that node has a copy of this particular line of the memory, or it will be 0 if it doesn't. And it will also have a status that says, is it a shared copy, a read-only copy? Is it a writable copy, an exclusive copy? But basically, the idea is that we'll have for every, so every address in the system has some home memory, right? So think of, you take the addresses overall, these are physical addresses, and you use the high order bits of those address to break it into blocks that one block per node in the system. And then for each of those sort of 64-byte lines worth of stuff, we'll basically have a data structure that says where all the copies of them are and are they and what the status is. Okay, so anyone starting to get worried here? Yeah.
If you have a lot of processors, you're going to have like a ton of bits each line.
Yeah, so imagine P processors, you have to have P bits there. But what's even scarier? Yes?
No, each time you load something from memory, you have to go to each of the processes. You have to get the bits like for all the directories, and to go to each of the processes and update their one corresponding.
No, it's actually not that bad. Because every block, every 64-byte chunk of the memory space has some unique home where it lives. And that can easily be determined based on its address. So you don't actually have to go across every one to do it.
I mean, you have to go to the ones that have the bits that set and go to the processors and update.
Well, you're jumping ahead of me a little bit. So, okay, we'll get to that. Yes?
The size of the directory?
Yes, the size of the directory. Remember when we talked about caches and you did your cache lab in 213, you had this kind of information about tags and dirty queen bits and stuff for every line of the cache. But now we're talking about for every line of the memory, right? And so let's do we'll go through the protocol and we'll see what this, it's a useful first step, but we'll see that we have to do something else to make this practical. But let's talk more about sort of the mechanics of how this would work then. So imagine that like I said, you can think of that every sort of 64-byte chunk of the address space of this physical address space of this machine has some home. It has some designated processor and some part of the memory where that nominally resides. That's where its sort of long-term copy is. And all the caches are just making temporary copies of it. So imagine then that processor 0 wants to make an access, a read access to some chunk of memory that's held by processor 1, and it has a cache miss. I mean, it might just find it in its local cache, and that's great, but let's assume that it's a cache miss. So like I said, it will be able to tell based on the address where to go, and it will send a request, a message over some type of a network. Something that's got to be a very fast network, though, like way faster than something you could do using Internet Protocol. And that processor will say, OK, that's good. Actually, nobody else has a copy of that right now. And so I'm going to send you a copy of it. And I'm going to mark you as having that copy. And I'll mark it as a read-only copy so that I could potentially share it among others. And this same thing would happen if it actually had multiple outstanding copies of it as well, as long as they're read-only. But imagine that the read happens, and actually processor 1 has, well, actually processor 2 has a copy of that line, and it's dirty, meaning that the copy that's in the memory here is not up to date, perhaps. So now it's going to get a little more complicated. What it would do in one version of it, and we'll look how to sort of refine this, is say, so this is called the home node for this block. It will come back and it will say, I'd like to help you, but in fact, you've got to go talk to processor 2 about this. And then processor 0 would send back a message saying, hey, processor 2, I want a copy of that, and I want it. I'm going to read it. So just like with the Snoopy bus protocol, now processor 2 would have to mark its copy as read-only. And meanwhile, processor 1 would figure out that it was creating a new read-only copy was being created, and so it would mark it as shared. And then this would respond with the data. By the way, this is all glossing over. As you know, with concurrency, things don't always happen just in order. It's quite possible that while all this going on, processor 2 decide to evict its copy. All kinds of other junk can happen, and processor 1 might get other requests for that same line. And so you can imagine the actual implementation of these protocols requires a lot more work than just drawing a few arrows on PowerPoint slides or Keynote slides. But you get the general idea that it's now, instead of that just a sort of 1 or 2 bus transactions that let me kind of have everybody change their state and respond because they're all kept in this sort of very synchronized world. Now it's all distributed, and I have to get things by sending messages around and having sort of requests and responses go on. And a similar thing would happen if processor 0 wanted a writable copy. And let's say that this line is being shared across several different processors right now as read-only copies. Then what would happen is the home would send back a list of all the processors that have copies of this line now. And processor 0 would send over invalidation messages to all of those. This is what you were worried about, I think, right? The idea that you'd have to somehow tell everyone if you needed to invalidate something, somebody's got to tell all of them, hey, you invalidate this, right? It's not a single. The good news is you only have to send to those who have copies of it, not to broadcast to the whole system. And meanwhile, it would actually have to wait until they all send back acknowledgments that they've done their invalidation. Otherwise, you could end up getting some inconsistency going there, right? As you saw before, if you have different copies and not a consistent model of who has rights to which copy, you can get in big trouble. And only then can it actually start doing the writing to that. So you can see this protocol gets, and like I said, if you add all the different concurrency possibilities in there with evicted lines and conflicting accesses and things, this gets more and more involved. But the good news about this is that you don't have to broadcast to the whole system. If there's 1,000 nodes in this system, not all 1,000 of them have to see every single memory transaction. It only has to, these messages just target the directories on the nodes that actually are have some reason to have a copy of this part of the this data. On writes, you see that the scalability issues have a lot to do with how many sharers there are. If there's just 1 or 2 sharers, you can just send targeted invalidation messages to them. But if you have 100 of them, then again, the cost of sending that many messages, unless you have some kind of broadcast capability, is fairly high. So the similar data that you saw before, there's been a lot of research on sort of benchmarking applications for what are their memory characteristics. And so you can see this example of these 3 applications. And here the question is, what percent of the writes have what number of sharers, where 1 means that the local processor is the unique holding copy. 0 means that it's a write to some something where it's completely uncached. So the more typical case is that you read something and then you want to write it. And so the strong peak here is at 1. And it kind of tails off from there. And you'll see that, for example, Ocean, you have 81% for 1 share and 15% for 2 and 3% for 4. And then it drops off very quickly after that. Barnes Hut is not so good. It's 48%, so about half of them are local. And that means another half are non-local, and there's a pretty long tail here. So that tells you that, and even though this is like 0.1%, 0.2%, remember these are relatively expensive cases where you have to send a lot of validation messages. So 0.1% can add a lot of cost to the overall problem. So the main point being that these, you can sometimes get very good locality and small number of copies, but not necessarily. And so you can sort of break down the sort of common access patterns into a couple different classes. One is mostly read objects, so things where there's data, but most of the activity on it involves shared reading. And you can imagine a lot of cases you've seen of that, of say, your set of circle parameters in assignment 2, right? That you ended up having a lot of threads rendering those circles, but it was all read-only data. You'll see migratory objects where it's sort of something gets constructed and then it ships over and moves to another processor which works on it for a while. And so things are sort of well-behaved that, sure, there's some effort involved in transferring data from one place to another, but it's relatively infrequent. And then there's other objects where there's a lot of fighting for it, but it moves around so quickly that it doesn't have much time to pile up a bunch of sharers on it. So again, that's somewhat expensive, but at least the count of sharers is relatively low. And then locks that are relatively lightly used aren't a problem. But as you can imagine, you can get locks if there's a lot of locking where a number of processors are trying for that lock. Typically, you implement a lock by doing reads in a spin loop until you see some flag get raised, and then you try to write it real quick. And so you end up, if there's K processors, they'll end up with K copies that they're spinning on until one of those, that copy will get invalidated across all K cases. One of them will manage to get a shared exclusive copy and grab it, and then the rest of them will start reading again. And so you're sort of doing a lot of cases of K shared copies, one giant invalidation, one write, and then K shared copies again. So that's fairly expensive. And so what you can imagine is, well, maybe for this we don't want to just use the sort of, we want to be a little more clever about how we implement locks so that we're not stuck in this case. And often what happens is you have to adapt your software to make use of the characteristics of the hardware. Okay, so let's talk about this problem of how much space all these directories would require in this scheme. And as I mentioned, the challenge is potentially this directory isn't based on the cache lines, it's based on the memory. And so imagine then you had a 64-byte cache line, and there were 256 processors, and there was m bytes of memory. So let's multiply it out. We get to take the m bytes of memory and divide it by 64 as the total number of lines of memory that we have to keep track of. And then we need roughly 256 bits for each directory entry. 256 bits is how many bytes? 2 to the 8th, 2 to the 5th, 32, right? 32 bytes per entry. So you can think of it that you need 32 bytes worth of stuff to keep track of 64 bytes of data. Right. So you have about half as much directory memory as you do your main memory. And by the way, this directory memory better be in SRAM, not in DRAM. So you can't really build it. So in general, you could say that the case I gave then is a 256 node system. You have sort of half as many bits in the directory as you do in the main memory, so 50% overhead. And of course, it's smaller with smaller values of p, and it's larger with larger values of p. So what could we do about this? Well, there's a couple things we could do, easy things. One is we could increase our line size to be bigger than 64. So why would we be worried? Why is that not necessarily a good idea? Yes?
Increases the chance that you'll have collisions, right? Multiple processors at the same.
Yes. So more collisions, and in particular what they call fault sharing, right? Where there's two, and we showed examples of that in the last lecture, that there's two words of memory that happen to reside in the same cache line, and they're unrelated to each other, and they're heavily used by different threads. So basically, these two threads would be fighting back and forth for that same line of data. What they're actually using is completely disjoint, but an example was given of performance counters. But that's a real problem. So increasing the line size is sort of an easy fix, but might not be a great idea. The other way would be in various different ways to reduce how big P is, right? Various sort of like we saw hierarchies of aggregation. And this is actually done where clustering multiple processor nodes using, say, a bus-based coherence protocol at the local level, and then using a scheme like this at more of a global level across this interconnection network. But now what we'll do instead of the sort of obvious sort of just cutting the corners in various ways, let's talk about ones that are sort of fundamentally different, how they store the information. One is to recognize that, hey, look, there's sort of two main things we really want to take care of. One is the very local case of maybe a handful of sharers, and the other is the global case where there's potentially sharing across the whole system. So you can imagine having a dual approach where you have a directory structure, but instead of a bit for every possible sharer, you basically have a tag indicating which sharers there are, but you only allow, say, 4 of them or 8 of them or something like that. And if you had a 1,000 processor system, 10 bits per pointer, say 4 of them, that would be 40 bits, which is a little less than before. And then what you'd say is for things where there's more levels of sharing, you could either just say, sorry, you can't do it. Basically, just like a cache, you limit how many copies are allowed, and you force evictions for ones that are, if you need to have somebody else have access to this. Or you could just have in your communication system a sort of broadcast capability that would say, look, this is shared across the whole system. Every time I invalidate, I'll just broadcast to everybody an invalidation message. So you can imagine sort of hybrid schemes like that. And that's what these describe. And these are all actually interesting examples of pretty smart sort of engineering thinking about how to make trade-offs. It's called optimizing the common case. So in general, if there's something that happens a lot, you want to make sure that goes fast. But something that happens sort of only once every 1,000 cases or something, you can fall back to slower and cheaper mechanisms. And so, again, the way you do this as an engineer designing these systems is sort of run a bunch of benchmarks, see what performance impact you get from sort of various compromised systems, and see what the kind of cost benefit is. Okay, but let's look at other ways that we could reduce sort of fundamentally the number of entries in this directory. And one is an idea that of what's called sparse directories. And the idea is that this is actually, I'm going to throw this out as an example, and we're going to see, whoops, this might not actually work. But what if you said, well, we actually don't need a directory entry for every single part of memory across the whole system. We just need one for every part of line of the memory that's resident in some cache somewhere. So we could sort of allocate an entry in a directory in the home node for this block of memory whenever there's some sharer somewhere, but ignore the case where there's no sharers. The problem is it turns out that it won't really scale if we potentially could have, because the memory blocks of one node might actually be spread across all the caches in the system, each having a unique copy. And if you work out the numbers, that can be a lot of copies and a lot of directory entries. But again, you could imagine a scheme that limits it just like a cache limits it, that says, look, I only have some number of directory entries, and if I need more sharing than that, I'll start evicting things from caches elsewhere. So various other schemes you can think of as trying to cut down on how many directory entries you need. Here's another scheme that's a little bit more extreme, though, which is basically you build up a chain of a doubly linked list chain that describes all the sharers of some block of memory. And so the home node sort of is the head of this list, and it creates a linked list through all the different nodes that are sharing this entry. So how many of you have done hardware design? Have you ever heard anyone designing a doubly linked list in hardware? It's not so easy. So this probably is more what a software person's view of the world would be than a hardware person's. And you can see this would be a nice scheme in terms of compactness, but a pretty slow scheme in terms of if you have to invalidate, basically you'd have to, it would have to step through this entire linked list, which could be distributed across the nodes, of course, and each of them could sort of send out the next message. But there'd be this sort of sequential requirement for invalidation. And only after they're all invalidated could it go back and carry on with whatever you're trying to do. So there could be a huge latency involved in trying to convert a shared copy of some data to an exclusive copy. Huh. It was a pretty good question it was asking. It said, did you hear that? It was asking something. I don't understand what you mean by exclusive. So, okay. Let's look at a little bit of tweaking of some of these protocols, though, because these protocols in some form are what are used in directory schemes. Oh, I'm sorry. This goes back to that linked list, that our original scheme allowed one big blasted out invalidation to all the targets. And with this, what we'd have to do is sort of plunk along one by one, sending out invalidation messages. So that's what this shows. Let's look at, so the first thing we're looking at is various ways we could reduce how much data structure is required. Another is, let's try and sort of squeeze out some of the latency in the coherence protocol. In particular, you recall that the previous scheme required sort of this on the critical path were 4 levels of communication. The initial request to the home's response, the request for the data from the holding cache, its response, And in the meantime, since this is converted to shared, it will send its copy of the cache line to the home processor, so that now we want it so that when it's a read-only copy, that the version in the memory is a clean copy, is a reliable copy. But that doesn't have to, that can be done, as you can see here, in parallel to the response to the initial processor. And if you think about it, it's not too hard to sort of squeeze out one more level there. If you let the home node, instead of sending back to the processor, for it to send the request to the holding processor and say, hey, look, give me your copy, make it shared, and by the way, while you, and send it back to me. And so it would then send it back here, and then this home processor could respond with the data. Or you could even squeeze it more if this home processor said, give me your copy, and while you're at it, send another copy of it to processor 0, then you could reduce these transactions. So you can imagine schemes that by adding a little bit more capability to what kind of messages you can send around would give you fewer accesses. So now let's look at some actual examples. This is the iCore i7 is sort of the main line of processors right now for Intel, including I think the GHC machines are all i7s of some slightly old vintage. And the Shark machines at 213 are. But you see that it's what I described to you before, that there's an L3 cache. There's 2 levels of cache at each core. And then there's some type of interconnect which gives you this, essentially a broadcast capability. And then there's an L3 cache that's shared across them. And so the cache coherence work takes place between the L2 and L3 levels of the cache. And that's sort of the way I described it before. And this thing is limited in how many processors actually are fitting there. And it's possible to buy a multi-socket system, meaning that there's multiple chips that all plug in, and maintains coherence across that. And that's done using one of these ideas of a sort of hierarchical set of buses, that there's across, when you connect multiple ones of these, and that's, by the way, the GHC machines must have 3 of these, right? Because it's got 12 cores per node. Is that right? People remember? I think that's what it is. So basically, then there's this other layer in the hierarchy that's used to maintain cache coherence across these different subsystems here. And with directories and agent. So an agent here is sort of keeping track of what cache entries that are from the memory of this processor and are being held in the caches in this other processor. So there's sort of has to be some sort of a way to keep track of this sort of cross product of memory on one side and caches on the other. Question?
That line that goes on that slide.
Sorry. Yeah. Right, that's exactly right. So, right, it's not the distributed one you saw before where each processor has its own little chunk of its own share of the memory. You can think of it as this huge complexity here is some combination of DRAM and cache. So at this level, you can think of it as, this is the cache for something that's like a processor, except it's a bunch of them. and then this is the memory. So it looks at scheme, except that it's sort of, you have to sort of pull out further up the hierarchy to understand that. And that's common. There's a couple of reasons for this. One is just from a manufacturing point of view, this is all one chip. It's a big chip. And this is all one chip. It's a big chip. And they can, spit out those chips out of their fabs in Oregon pretty fast, and then they can sell you the different chips, and then you plug them in. Or you as a customer could just buy one chip's worth, and so partly it's done that way, but also partly you can't fit any more stuff on a chip than what they've got. There's a question? Yes?
So to clarify what you were just saying, is this a UMA or NUMA?
It's a NUMA, yep. It's a NUMA. It would, one of these worth is not a NUMA, right? Because well, except for the fact that you can think of anything with a cache as non-uniform access, right? But all the memory is so it wouldn't be considered a NUMA though, because all the memory is sort of here, all being guarded by this L3 cache. And so it's one common memory. So it's not a NUMA in the sense that I described. This becomes a NUMA, a sort of two-way NUMA in that scheme of things, right? These are good questions, by the way. Yeah, so I think the GHC machines basically have 3 of these. So it ends up with 12 cores, each of which is two-way hyper-threaded. Yes?
Don't the GHC machines have Xeons instead of I7s?
The Xeon is it's really hard in Intel to figure out what the heck is inside of a box based on its name. This is a general statement. Because they basically trademarked a couple of names a while ago, Pentium, iCore, Xeon, and instead of making up new names, they just mix and match these names in arbitrary ways. So the Xeon just means that it's designed for server class applications. And there's been multiple generations of Xeons over the years. The i7, Core i7 is a particular category of processor, and it actually exists in a lot of your laptops here have iCore 7s in them. They're just not as beefy an iCore 7 as these are. So iCore 7 kind of corresponds to a class of machine, but even within that, if you really want to know, you have to know what the internal name used at Intel when they developed these chips was. Is it a Broadwell or a Haswell or a Sandy Bridge, or all different names of iCore i7 processors. And those are what actually determine what's really going on with the thing. So it's actually really hard to track this stuff down. There's many Wikipedia pages that cover this, though. And basically, by the way, if you ever on a machine, if you go to print out the file called /proc/CPU info, right? It will say, it will give you a model, ES something, something, something. And you can Google that and actually find out what's the real processor inside. And so that's a pretty useful thing. So just to convince you that I'm really not kidding when I say it's really hard to figure out is Intel has this class of machines. In fact, this is what late days is. Actually, it's a set of them, are what are called Xeon Phis. And a Xeon Phi has absolutely nothing to do with any other kind of Xeon. It's just a trade name, a brand name. And it's Intel's sort of move into it's trying to compete with GPUs, basically. In fact, this started as a project within Intel that was called Larrabee, that they were going to try to create a next generation really a graphic processing unit, not a computer unit, that they thought would be able to compete against NVIDIA and its companies. So the machines we have on the late days their internal name is Knight's Corner, and you have to know that to know what the heck's going on. And they're designed to have 61 cores. Now, I actually counted this, and I came up with 62, which I believe is actually on purpose, that they basically, because you'd go 61, where did they come up with 61? It's a prime number, right? So I think that one of those is a spare, that they can, post-manufacturing, they can test all the cores, and if one of them's bad, they can basically program around that and still have a chip that they can sell you for money, because these are really big chips. And so in a big chip, the biggest problem you have is if there's one defect anywhere and that kills the whole chip, then it becomes very expensive. So by having some defect tolerance means that you get a much better yield. And that's important. That's yield equals profit in the semiconductor world. So anyways, these things are on the ones we've got are called Knight's Corner. They're about 3-year-old designs. In each core in this is basically a souped-up Pentium processor, a Pentium from 1995 processor. And it has 4-way hyperthreading instead of the 2-way. Can anyone imagine why in a NUMA system hyperthreading might be a good idea? Yes, so that's just it. That the memory latency in a NUMA system is much longer. And so if you can hyperthread, meaning swap between multiple threads at a very low level, then when one of them stalled waiting for a memory, another thread might be able to execute. And so if you can do that quickly enough, which is what hyperthreading is, then that's a good thing. They also have built into them, into the Xeon Phis, vector units, the SIMD units that you've already seen. And the main point is that they're cache coherent across the whole system here. So the Knight's Corner system overall, if you were to be totally optimistic about sort of getting all of these SIMD units going full blast, doing single precision, because that's twice, you can do twice as many of those as double, you could nominally get 2 teraflops out of this chip, which is not bad. It's actually not as good as our NVIDIA GPUs, but it's pretty decent. The maximum this design memory that you can plug in that it can support, obviously it's not on this chip, but elsewhere, is 8 gigabytes. And that's not very good. In fact, in the supercomputing world, they talk about the balance of a system being the ratio of how much memory you have divided by how many floating point operations per second it can do. And this is actually really bad. You actually want 1 byte of memory for every flop. That's considered a balanced system. And this one is 0.004 bytes of memory for every flop. And that's not good. But it's still, and it's a big chip, and it's a big high power thing. But it's actually an interesting perspective on how this works, because in some ways it's a much simpler design from a cache coherency point of view than these other directory schemes we've seen. And the reason is because it has connecting these cores are logically organized. There's a ring network. So when you send, it's bidirectional. So when you're sending messages from one place to another, you can send it in either direction around this ring. But one good thing is if you want to broadcast, you can just sort of circulate a message clear around the ring, and it will get to everyone in fairly short order. You'll see that there's, this picture isn't really scaled, that there's basically the memories of this, and DDR is the DRAM. These are the memory controllers, the MCs. And so there's 8 memory controllers, each of which can handle a gigabyte of memory. And one interesting thing that's possible, because this thing's on a single chip, is that this network is actually a really fat network in terms of how many bits you can send around this network all in parallel. So think about that. In each direction, you have a 64 bytes, so 256 bits of data. So a whole cache line is basically running around this network, each bit on its own wire. And then this is for the address information, and this is for the coherence, cache coherence control information. And that's bidirectional. So this thing is over 256, over 512 bits wide. So do you know, like, for a big chip, about how many pins you can get on it? So a big chip would have 1,000 pins. So you couldn't run this kind of scheme across multiple chips. You couldn't dedicate that many pins to it. So this is the kind of thing that there's a huge advantage to in a system design. If you can get everything onto a single chip, you can do some stuff that you would never be able to think of doing across chips. So one interesting thing about this is that the cache control scheme then looks a lot more like the Snoopy bus protocol than the directory-based schemes we've seen before. That these are called directories, but they're actually just controlling the information. They only have information about what is stored in this particular local cache. And so what happens is if there's a memory read by a processor, well, first it will check its own local cache, and if it's there, then fine, nothing. Otherwise, basically it will send a message over around the network to the home node for that particular block of memory. And if that block is in the let's see. Oh, I'm sorry, no. I'm wrong. It will say, basically send a message around saying, hey, any of you have a copy of this line in your local caches? And if one of them does, then it will just forward that request directly back to it. So that scheme, and it also make the appropriate change in its status if it has to have multiple shares. So the point is there's not this directory like we saw before of one place keeping track of who has copies. Instead, each directory, so-called directory here, only needs to know about the copies in its own local cache, which is really the same as what's in a cache controller anyhow, right? It just has to have the status information. It doesn't need to know who the sharers are. And similarly, if it has to invalidate, it can just send an invalidation message around this ring, and all the caches around there will invalidate their copies. And then if none of the caches hold a particular line, then it will have to do another message around the ring because you saw that the memory controllers are also plugged into this ring. And so that memory controller will then supply the relevant part of it. But at worst, there's sort of 2 rounds of this ring to transfer data because it's more or less like we saw with the Snoopy bus protocol, right? That by sending a message around a ring, you can kind of broadcast or collect information from across the whole system. People see that? So that's a nice simplifying thing. Now, it turns out that Intel has dreams of building bigger systems. Oh, I should mention that this Knight's Corner, of which we've got a handful, off in China, the world's fastest supercomputer has 48,000 of these. Right? It's a 16,000 node system, each with a real Xeon CPU, and 3 Knight's Corner GPUs of these things. And it's rated at 22 petaflops, 22, 23 petaflops on the benchmark that's used for ranking supercomputers. So it's about twice as fast as the biggest computer in the US, which is at Oak Ridge, and is based on NVIDIA GPUs. But most people agree that it's a bit of a stunt, this machine, that they managed to build a machine that worked just fine for this one benchmark they use, which isn't really very reflective of what's used in a lot of applications. And it's actually, they built it several years ago, and it's been the #1 on the list for all this time. So, but the point is, they wanted to then double the size of the system, but the US government said no to Intel. They couldn't export that many more of these chips to China. So the next generation of Xeon, which I think will come out this year sometime, first of all, it's a nicer looking chip in my mind. These are like little blocks, where those other things, they looked like, oh, we've got these cores, let's just splat them on a chip as any old way we can. And so this thing has 72 compute cores, and they're based on the Atom processor, which is, as you know, Intel's attempt at a low-power processor to compete with ARM. Not very successfully. But in other words, a processor designed specifically to be lower power, and that's important when you put this many on a chip. Again, 4-way hyperthreading, 2 of these SIMD units using the next generation of it, which is, they call them 512, AVX 512, because it's 512 bits, which is 64 bytes worth of vector size. And then what they do is they take 2 of these cores and they group them in a pair to give a compute node. And in this picture, the blue dots are compute nodes. And you'll see that also connected in there are other nodes that provide the interface to the memory. And there's 4 of these memories, they call them MC DRAMs, that are more tightly packaged and therefore faster access. And then there's the big RAMs out there that are on different boards, presumably, or further away at least. And so these are potentially very large but relatively slow. And then you can either operate these DRAMs as like a cache for the big RAM or as a separate programmable memory. And then, so now you see that the idea is to be about 6 times faster, at least in peak, than the Knight's Corner chips. But I think the bigger advantage is access to a lot more memory. And then the overall structure on the chip then is more of a, not a ring-based system and not a bus-based system. So each of these nodes now is either a computing tile or a memory controller. And you'll see it's all organized as a network, a grid, in which you can send messages either up and down or left and right. And so to get move data or a message from one point to another, they go first in the Y dimension and then in the X dimension to get to a particular place. So it's like a network with this particular grid topology. And like a network, there's no centralized and there's no broadcast capability. So the only papers on this are very vague, but at least you can infer that it looks like more of a traditional, a true directory-based coherence structure, where you have to keep track in some form of, somebody has to keep track of where all the copies of particular memory are so that they can access them appropriately. So that this is going to be used in the next generation of supercomputers that are being delivered. I think the one to Argonne is from Intel. I don't remember. There's a recent procurement called the Coral procurement. I spent last year worrying about supercomputers, so I might know more about this than is too much to be. I know just enough to be dangerous. So anyways, so these are sort of Intel's next generation of chip. And it's the point being that it's actually, I guess they must have found that their ring was too much of a sort of central bottleneck, couldn't handle as much traffic as they were looking for. And so they had to go to this grid. But now that raises the stakes, and now they're going to need some more general directory-based scheme to keep the coherence. Question?
Go back one second, please. There's a limit that says access to up to 384 gigabytes of RAM. Is that limit determined by the directory sizes, or is there?
I don't know. You'd have to. I'll post a pointer to the slides. The only presentation I've seen on this are extremely limited. So I would think they would not be able to.
Because it's not like a 32-bit, 64-bit. So there must be something limiting this.
I would have to guess that they're not internally trying to do coherence across these big memories, because that's just too darn expensive. I think the coherence is in these memories, and then these memories serve as caches for these big memories. Because it's like 380, every scheme we've talked about would not scale to 384 gigabytes. So that's actually something that would be worth tracking down and understanding.
Are directory sizes usually a limiting factor in the access to memory? Not just this chip specifically, but is that something that the chip makers consider?
So, by the way, it's interesting that you mentioned the chip makers. Historically, these big shared memory systems were where each node was multiple chips, and the directory structure would be a separate set of chips from the processors. So part of it is, and this has been true for Intel over time. Intel started off as just making little controllers for calculators, right? So. But now they've become a computer company, and most recently they've become a supercomputer company because you can get sort of supercomputer power on a single chip. And so now they're having to introduce these schemes into it. But the directory sizes are definitely a huge factor in these schemes and how you organize that. As you saw, that sort of naive schemes, you can easily require almost as many bits of memory as you do of directory as you have memory bits. Other questions? Okay, so yes.
Also, is it possible, like, for some kind of scheduler to like directly do certain calls, so they don't have to do cache coherence between like cores and stuff?
So the question was, is there a way that you could basically not use, what about just skipping this whole cache coherence stuff? I'm generalizing your question. And in fact, there's quite a few machines out there that are not cache coherent. The big Cray machines are not cache coherent. So they allow you to access memory, but it's up to you, the program, to figure out, how to deal with, potentially multiple copies of an object. There's other schemes that are sort of a hybrid where there's a little bit of hardware and a lot more software to maintain. So there's sort of software-based coherence schemes as well. So there's, this is just skimming the surface. There's many different approaches to this. Yes?
For those kind of systems, would you have to explicitly say when you want to write to memory versus the cache?
Let's see. So yeah, I think that some of them, the extreme version of it is instead of a cache in the usual sense, you have what's called a scratchpad memory, meaning it's fast memory under program control. And you'd load blocks of that and explicitly write out blocks if you wanted to. So that would be the extreme version. And then I think, I don't remember all the details on some of the big crays, but you can imagine various other schemes people come up with that sort of try to balance between relatively expensive hardware versus sort of trying to put some of the complexity up into the software, either at the application level or more, sort of system level software. In fact, the world's largest supercomputers, Tianhe and the one at Oak Ridge. Titan, thank you. I'm trying to remember. It was called Jaguar, and now it's Titan. Are not even shared memory machines at all. They have nodes, and like a node in Tianhe 2 has either 1 or 2 Xeon cores, I forget how many, and 3 Knights corners. So it has shared memory within the Knights corner chips. It has shared memory within the cores of the Xeon chips. But across the system, it's not a shared memory system at all. And so you'll often, as you get to really big scales, they pretty much discard the idea of trying to be cache coherent across the whole system. And so you people are mostly software people. You can imagine the programming challenges of this. That, like for the one at Oak Ridge for Titan, basically you write CUDA code to run their GPUs. You write OpenMP code to run their multi-core processors. And then you run MPI, message passing interface code, to talk between them all. And then you take an application and you say, I want to sort of move this part onto the GPU. Well, you have to rewrite all your OpenMP code into CUDA. And I want to move this to message passing. Well, you have to take all that shared memory stuff, multi-threaded stuff, and start sending messages around. So it's quite a mess to actually program these things, especially tuning performance-wise. You can see that just balancing across that's a huge problem. But that's sort of the reality of the systems that people know how to build today and what we're stuck with. So this shared memory model is a nice model and very convenient especially for data structures that are sort of irregular, like the graphs you're working on in this assignment. But it comes with a cost. And so you can buy a very large shared memory machines from a company called SGI. They're pretty expensive machines, but there's some applications where it's really the right thing. So I guess, by the way, that I think part of the reason why this class has so many students nowadays is a lot of this stuff, the number of people who actually program these really big machines is pretty small, but more and more you're finding these capabilities on single chip or single board systems that you'd find in a workstation or something like that. Let's see. Let me just go back over the last slide here. So just to wrap it up then, so the main point we saw is this idea of broadcasting. Maybe you could scale it to something like Knight's Corner. So 61, using that ring, has a lot of the properties of a single bus, sort of a broadcast capability. But that's pushing it. And so instead you move up to schemes where there's some type of directories keeping track of who has copies of what. And the sort of most obvious schemes for that are very problematic in terms of how much storage they have. And then the other problem is sort of how many messages, how much message traffic has to get sent around, how much of that can be done in parallel, how many steps does it take. Those both affect the total amount of network traffic and the latency of the memory accesses. So these are parts where the There's no easy solution for it. And you see these different systems have come up with various kind of hierarchical schemes to handle it. So that's it for today then.